how do we feel about moving on to the discussion section?
I think it's a great time to move on to the discussion sessions, which will go until 1:15.
Okay.
So now we can entertain any questions that people might have for our speakers, or we can kind of look at some synergy between many or all of the talks. If there are questions that people want to put forward, you can do it in the chat. You can raise your hand. You can even unmute.
I mean, I guess one thing that I could bring up, because I thought it was interesting, just I know myself and Ziyu are both kind of doing MD work. And I just think, you know, sometimes some of these simulation methods are great, but then the problem is that the people who do MD are the only ones that really understand the MD work. And then sometimes its connection is lost to how to project it up to more accurate time scales or more accurate dimensional scales. So I guess, I mean, maybe it's a question for Ziyu or anyone who does modeling similar to that, but, you know, what kind of efforts are put in to try to make sure that what you're simulating has experimental relevance, or we can compare to those? Because I noticed that when I do these talks, often the questions become, you know, have you compared to this experiment, or are you talking about a geological scale? And then the answer often becomes, no, I'm talking about like a picosecond scale. So it's a huge gap. So I just think thinking about how we can tie simulations into experimental and then ultimately actual lunar data, I think is an interesting concept. It's just a thought, I guess.
So Liam, I want to follow up on that. So it was very unclear in either of the simulations what potentials were you using, because in the end the interaction potential is what is very important, and you were looking at different targets, so the interaction potentials were likely not be the same. But could you comment on that?
Yeah, definitely. So I guess your question is totally relevant, because I think for any MD study, the interatomic potential is basically the crux of whether it's going to be accurate or not. And I think one of the challenges in talks like this that are not specific to MD is to try to decide how specific do you get into MD related topics without kind of losing the audience. From the point of view of mine, what I used was a reactive potential. So it's a REACT-FF. I used the same one for all my models. I think that's important in the sense of you want to make sure that the differences you observe are not due to just changing the potential type, and you want to do some kind of a verification. So the potential that I selected had already been verified for silicates, sodium silicates, and silicates containing hydrogen, and both for amorphous and crystalline. And just for the group, I guess those are often verified compared to experimental or density functional theory data. So DFT data is probably like a scale down. So yeah, that was the interatomic potential I used. And I guess, and the other thing that I could note is that when I talk about discrepancies found in previous results, one thing that's important to note is that all those previous MD studies that I showed also use the same potential that I'm using. And that was an important flag for what's going on here, because often when you see a difference in simulations, it's often the parameters used, and typically in MD, that's ultimately we used a different potential than them, so our results were totally different. But when I saw that all those studies used the same potential, then that flagged for me that there's something going on in the methodology, or some reason why we're seeing these like orders of magnitude difference. And ultimately, I believe that that's essentially not accounting for the diffusion mechanism, because we often think of diffusion as this constant motion. We sample for long enough, we'll get it. But if the diffusion is just intermittent jumps, which at low temperatures are very, very rare, then you have to sample for long enough that you're observing enough jumps that you're not at the mercy of just statistical sampling. So I guess that kind of hopefully answers your question a little bit.
It answers it quite well. I have a little bit of a follow-up. So we're looking at this problem with respect to hydrogen buildup in glass waste forms for radioactive storage.
Sure. Okay.
Turns out that the barrier heights for motion and proton transport are not the standard lattice vibrations that you would consider. It's actually the dangling OH bonds that are formed, and then you get these layered structures in a lot of the glasses, or within the pores, like we're being discussed with the ice, and so those subtle structural differences actually govern the energetics. Is there a way for you to sort of put that in as a next step?
Yeah, definitely. So I guess the key there is when you talk about dangling OH bonds and things like that, you're essentially talking about traps and you're talking about reactions. So the key is to use an intertone potential that can allow for bonds to form and break, and you're not just at the mercy of something that's kind of fixed. So I think there, yeah, definitely, because what you're basically referring to is you're essentially saying, I think at least, is that the energy or the activation energies that need to be overcome, you're seeing are heavily dictated by these dangling bonds. So yeah, you just need to simulate with something that can allow these bonds to form and break. So yeah, I think so. It shouldn't be a problem.
All right, you had posed, Liam, a question to Zhu. Zhu, you want to respond?
Sorry. Yeah, thank you so much for the question. Like, first of all, the timescale problem, I think that's pretty important because usually, like in planetary science and also in astrophysics, astrochemistry, usually the timescale is like million years. Well, we have the molecular dynamic simulation in this timescale, picoseconds or even femtoseconds. Yeah. So what I think we can do is to limit some, create some like artificial conditions, or like using some trick to simulate those kind of like space varying process. Like for example, when I was doing like implantation process, for the specific area I used for the sample is only like about like in the scale angstrom square. Yep. So if you consider the flux of the solar wind to the PSRs, so usually there's only one implantation per day. So if you make sure you relax the surface to the original temperature, then the implantation and relaxation could represent 1 day. Yeah. So in this way, you can like continue in the implantation process, and making sure each implantation won't affect another the other implantation process. Then you could like simulate like a real planetary science time scale.
Yeah, definitely. No, that makes sense too.
I mean, for other cases like micrometer impact, well, you know, for like 20 kilometers per second impact, the hypervelocity impact usually occur in a really small time scale, and I'm not sure if experiment can capture the impact process in about like picoseconds or even microseconds, but MD simulation can definitely capture the whole process. So I would say that's a good thing about MD, but another thing is like the relaxation time. Like, how long do you wait for the MD for the impact to relax? One thing I would do is like monitor the temperature. When the temperature is lower than the absorption temperature of water molecules, like 170 Kelvin or even lower, then I will see the relaxation is almost done. But honestly, I think that could lead to some error, but it could be some it could be some approximation. So
yeah, no, yeah, that makes sense to me.
Yeah.
When you're doing your impacts, I guess just one thing to add to that is that when you do your impacts, first is, are you tracking the sputtering too? And then the second thing, which I presume you're probably already doing, but you can use a dynamic time step.
Yeah, that's right.
Actually, let the time step modify, so you like limit the amount of motion between each step. That's just an MD specific idea that I'm not sure if you thought of. Yeah, and Micah, I know your hand's up there, so
yeah, I was gonna say Liam and Zhu. Let's go to Micah. I don't know if the question is you guys or but probably is. Micah, you're mute.
No, sorry, I was just playing with the reactions a little bit too much. I think I got a little overzealous there. My question was actually for Brittany. You talked about this a little bit in the chat, and I was wondering if you could go into it just a tad more on how you think this nanoferrous iron might be forming sort of deeper in the sample, sort of below the rims. I think you sort of glossed over that a little bit in the chat, and I was wondering if you could go into it a little bit more.
Yeah, thank you for your question. It's truly unusual that they're forming that deep, because our conventional understanding of the implantation depth of helium and hydrogen is like 10 orders of magnitude smaller than that. So like maybe up to 35 nanometers. And Morgan brought this up, but there is that study, Quadri et al. 2015, 17, talked about the diffusion of oxygen being anisotropic in pyroxene, and it's different in an orthopyroxene versus a clinopyroxene. And so one of the things I was curious about was to determine the orientation of these lamellae, because if we can determine kind of the orientation normal to the space weathering, we can figure out if oxygen is diffusing through and healing where hydrogen is getting to and kind of running into and forming and kind of nucleating the nanophase iron particles. So this could be a crystallographic effect. There could be ion channeling that could be bringing hydrogen deeper into the crystal. So yeah, this is a really interesting and weird texture that we saw.
But it seemed kind of clustered too, or was it really widespread? Is that just the image that it looked clustered in?
It might have. That's a good point. It really just kind of seems like bubbles almost forming like underwater and kind of like floating to the surface. They could be clustering. You could be getting like localized areas of like hydrogen nucleating bubbles, and then all the iron around that could be getting reduced. So yeah, we're not quite sure. What we would need to do to really test that would be to look using high resolution TEM to look at and if there's any local crystallographic like amorphization or structural changes in that area that would cue us into what was happening at an atomic level.
Cool. Okay, great. Yeah, thank you.
Thank you.
I had a question for you too, Brittany, while you're on. So between comparing the high calcium and low calcium pyroxene production of nanophase iron, is there a mineralogical or structural control at all that's also in play with them having different structural mineralogies? And does that give you any clue to how olivine might space weather in relation to pyroxene?
So between the high and the low calcium pyroxene, so the fact that there is iron 3 in an augite is not weird. It happens terrestrially. It can contain up to like 60-70% weight percent iron being ferric. It hasn't been found in a lunar pyroxene before, and I wanted to emphasize, and this maybe kind of gets into Shwai's follow-up question about this is primary ferric iron. We think it comes from a magmatic source, but the high resolution of the technique, these are only 20 nanometer wide lamellae, so we might not have detected it. It's just a detection limit thing. So the iron is maybe in a different crystallographic location in the augite than in the pigeonite. So like the M1 versus the M2 site, so there could be like cation site ordering, and because the M2 site is a 8 coordinated versus the M1 is 6 coordinated, so there could be anisotropy effects occurring there. But with olivine, it's kind of like sterically limited in its ability to incorporate ferric iron, and so I think it would have a more isotropic space weathering effect. And so I'd be curious to analyze other minerals that have structural anisotropy to see if they have this effect with iron.
Cool. Thank you.
Can I have a follow-up question, which is related to both, maybe all three of these? So the radiation chemistry community actually uses high doses of ionizing radiation to produce nanoparticles. And they can produce iron nanoparticles in a number of glasses containing iron oxide. So are you sure that they're, because of the dose rate with TEM is so high, are you sure that that's not happening at any level?
I would expect to see it happening everywhere. So the fact that it's not occurring in the pigeonite and it would just be happening in the augite would be a little strange, but the adjacent augite, that unexolved one I shared, didn't have any, or it had very little ferric iron compared to the exolved grain. So although they're adhered to one another, I'm not sure they have the same magmatic origin, but we do, you can certainly get beam damage in the TEM environment, but because we don't see kind of it happening ununiformly, and if we park the beam and scan across an area, we're not seeing any migration of these elements and evolution of the material. So we need to let it scan for a long time to really see oxidation effects like that.
Okay, all right.
I see what you're saying, yeah.
Thank you.
Thank you.
Shuai has his hand up. Do you have a question? Yeah. So thank you for the answer. The rest part of my question is like, I didn't pay attention. Did you do the experiments for Brainy? Did you do the experiments in a vacuum, like oxygen-free, or have you considered like a contamination of oxygen from the atmosphere?
So the high vacuum environment of the TEM does theoretically exclude oxygen, but it does, there is always a small amount of oxygen that could be occurring, and also the material could be degassing, although we do bake it prior to introduction into the TEM or degas it, so that we're not introducing any impurities. And I'm sorry, what was the second part?
No, I mean like when you did the space weathering, like radiation, irradiation, did you do it in a vacuum or in an ambient condition?
These are natural samples. These are return samples, so these are not experimental.
Oh, sorry.
Yeah.
I misunderstood. Okay, thank you.
Yeah, you're welcome. Thank you.
How about any questions for Mark Nottingham on cosmic ray exposure ages, or Raman Lachi on optical monitoring of dust? Any questions for them?
I have a silly one for Mark. Does your analysis process destroy the samples?
Yeah, it is destructive. So we split the sample, the grain initially from the soil, kind of basically mechanically fracture it as best as we can down the middle, take one part, and that's non-destructively analyzed for the chemistry. But the other part would basically heat it up in a vacuum furnace to release the gases from it.
And I imagine you wait for quite a while until you're pretty sure that all the gases are out. And then...
Yeah, so I think our analysis procedure was to basically heat it for 20 minutes. And then the gas that's released goes through kind of various processes of purifying it, taking out active gases that we don't want, that would interfere with our measurement. So yeah, I think for those samples, it was about 20 minutes that we heated them.
Thank you.
I had a question for you too, Mark. You had mentioned that the overturn rates at Apollo 12 were more significant, and I guess that's more significant to other Apollo landing sites. And I was just wondering how you compared it being more significant than other Apollo landing sites. Did you, in the past, make measurements on other Apollo landing sites or literature data, or is it really, it was just higher than other measurements at Apollo 12?
So I might not have explained that particularly well. It's not that the overturn rate is particularly high at the Apollo 12 site, but that work that I mentioned, the Costello et al. 2018, I think, they basically found that secondary impacts, so you have the primary impactor that forms the crater, and the material that's released from that forms secondary craters as well. And those secondary craters are far more important for the overturn rate. It basically revised down the amount of time that it would take to completely homogenize a given thickness of the regolith.
Okay, so you're actually seeing this gardening by secondary impact craters.
Yeah, they seem to be far more important than certainly the previous models had suggested or accounted for.
Neat. I like it when data can, help models, and models can help data.
I was very happy when our results lay between those values.
Any other questions for our speakers? We can even entertain questions for the lightning talks. quiet group on Thursday. We don't have the usual LPSC coffee or NESF coffee to get people awake.
Well, while people are thinking of questions,
Yeah.
an announcement by Mike that the plenary talk from this morning continues during our break. So if you're interested in Ryan Watkins's talk about maternal walls in STEM, then head over to the plenaries in 5 minutes. Did Tom have a comment?
Yeah, it was a question to Jeff. Can you give me your opinion on how useful the PCA approach is? Because there's a more sophisticated machine learning sort of algorithms out there. So I'm just sort of wondering, the question is, how good the data sets are and so forth for machine learning. I'm just wondering what your general opinion is on that.
Well, we use PCA, it's a great technique for, taking multispectral data and, looking at trends that, aren't apparent. With just multispectral data, it's easier to, look at those full spectrum. Machine learning could be the next step on the principal component analysis, but, someone's got to do the machine learning. There are plenty of spectra out there that you could get from eLab and other databases that could start. And I'm sure that would be actually a great project for undergraduate or grad student to begin with. But both PCA and machine learning have the fundamental flaw is crap in, crap out. If you don't understand what you're putting in, you can get unrealistic answers coming out. So we, been using, with PCA, testing what our components are, the best we can to make sure that, they align to something in the spectra and that we can interpret those changes in spectra with, the geologic process or space weathering process that's happening. So I think there is room for machine learning. It's just it hasn't been my expertise, and someone has to step in to do it.
Okay, thank you.
I have a question for Liam. In your simulations for diffusions, could you clarify if you considered the near surface electric field on the moon?
So we didn't simulate protons as much as we simulated neutrals. So we didn't apply an electric field because in speaking with my co-authors, basically most of the ions become neutralized once they make their way in through the surface. So we didn't as much look at the effect of the electric field, no. But now, with that said, the potential used, the reactive potential, does deal with the equilibration of charges. So any charges that would build up would be accounted for within the potential. But we didn't start with an ion per se.
Okay, thank you.
Or a proton, I guess, yeah.
And a quick question for you too, Liam, some people have used Monte Carlo simulation to do similar analysis. Can you compare, Monte Carlo versus the analysis that you're doing?
Yeah, so I think that's actually a really interesting comment. So, because one of my co-authors for this work is actually Dr. Farrell, and he's done a lot of the Monte Carlo work on diffusion of protons. And I guess the difference between MD and Monte Carlo is Monte Carlo, because it often uses distributions of diffusion coefficients and activation energies, it's kind of at the mercy of what you give it as an input. So I think what the purpose of the MD is to better inform the inputs of the Monte Carlo so we can better constrain what we expect the diffusion coefficients and the activation energies to be. So the limitation of MD is that it's so computationally intensive that you'd never be able to approach the scales you can approach with a Monte Carlo work. But if you can better inform the inputs of Monte Carlo such that you better understand the actual mechanisms going on, then you can make your Monte Carlo more accurate. So I think that's kind of how they connect.
Okay, cool. Thank you. I was wondering how that worked.
Yeah, sure. No, yeah, of course.
And now, perfect timing. We've come to the end of our session. Thank you to all of our speakers, and it's been a pleasure.
Yeah, thank you to
So-
Carolyn and everyone who put the plan together, this session together, and for our survey central help.
Yeah, it's been great discussions and super active in the chat, which I always love to see. So maybe I'll see you guys in the plenary, or if not, the poster session later today.
Great.
Yeah, thanks Jeff for co-hosting too.
Yeah, thank you, Alicia. It was nice to meet you.